Hello, in this video I'm going to talk about nuclear binding energy and mass defect and show you how you calculate the nuclear binding energy for an atom. So firstly, a thought experiment. Imagine this nucleus. This is a nucleus with 2 protons and 2 neutrons. So it is helium, and it's the standard isotope of helium, helium-4. If you wanted to split this nucleus into its constituent parts, you'd need to apply a force to each of the particles. They're bound together by the strong nuclear force. As the amount of work done is equal to force multiplied by distance, adding a force or applying a force and pulling over a distance means supplying energy. It would take energy to break the nucleus apart into its constituents, and binding energy is defined as the amount of energy required to split the nucleons, note protons and neutrons are nucleons, particles in the nucleus, to split the nucleons apart. So it took some energy to pull these particles apart, and by Einstein's famous equation, energy and mass are the same thing. If you supply some energy, you've supplied some mass. And that means if you were to put these two things on some imaginary scales and we could accurately weigh the helium nucleus and the mass of all the constituent parts separately, you would find that the right-hand side is heavier because we had to supply some energy to get to this state, therefore we supplied some mass. The mass of the 4 bits is always heavier than the mass of the particle when it's bound together. So if we consider the mass of all the particles on one side and the mass of the nucleus, we know we can look up the data for the mass of individual protons, and it's slightly bigger than the mass of one atomic mass unit. Don't forget that atomic mass unit is defined as 1/12 of the mass of carbon-12, but an individual proton is slightly heavier than a 1/12 of carbon-12, and that's of course due to this idea of binding energy. The mass of a neutron is ever so slightly heavier as well, and slightly heavier than a proton. So we can add up the mass of all the bits on the right hand side, that's 2 protons and 2 neutrons, and you get 4.03 U atomic mass units. Again, data can provide us with the mass of the helium. This number would have come from mass spectrometry. And knowing the mass of helium and the mass of all the bits, we can work out the mass defect. That's the difference between the two. The mass defect is all the bits subtract the mass of the particle when they're all together. You get a mass defect in U, and you can multiply by this conversion factor because 1 U is equivalent to this many kilograms. That gives us a mass defect in kilograms. Now we know the mass defect, we can work out the binding energy. The binding energy is defined as the energy required to split the nucleons apart. Because energy and mass are the same thing, the amount of mass defect is equivalent to the energy difference. Energy equals mc squared, multiply the mass defect by the speed of light squared. Note standard units for mass are kilograms, and this is the speed of light in meters per second. That gives 4.4 times 10 to the minus 12 joules. That's a very small number, but it's pretty big when you consider this is just for one nucleus. The electron volt unit is a better unit for comparing atomic energies. An electron volt is the energy given to one electron if it's accelerated through 1 volt. And that can be shown to be equivalent to 1.6 times 10 to the minus 19 joules. That's the charge on the electron in coulombs multiplied by 1 volt. So to convert from joules into electron volts, we're going to divide by this number, and that leaves 27.4 times 10 to the 6 electron volts. 10 to the 6 can often be written as million or mega. So 27.4 MeV is the binding energy for a helium-4 nucleus. Now it's often more convenient to quote the binding energy per nucleon. There are 4 nucleons here, 2 protons and 2 neutrons. And the binding energy per nucleon, therefore for helium, is 6.8 MeV by these calculations.